이번 마지막 섹션으로 QRT 주식회사 정성수 CTO님께서 고속 질주하는 자동차 업계를 위한 소프트 에러 평가를 발표할 예정입니다. 정성수 CTO님은 시스코에서 15년 이상을 근무하였으며 방사선으로 인한 소프트 오류를 완화하기 위해 업계 최초의 전사적 SEU 테스트 및 완화 프로세스를 개발했습니다. 현재 QRT에서 단일 이벤트 효과 테스트 및 분석 기술에 대한 R&D 활동을 이끌고 있습니다. 그는 17개의 미국 및 한국 특허를 보유하고 있으며 에이직 테스트, 테스트용 설계 기법, 소프트 오류 테스트 및 SEU 완화, 오류 주입 기법에서 60개 이상의 기술 논문과 프레젠테이션에 기여했습니다. 이번 발표는 반도체 산업계가 기술적 전환을 수행하는 데 중요한 문제가 무엇인지를 설명하며 소프트 오류 평가가 필요한 다양한 표준의 현 진행 사항, 평가 수행 및 평가 자료 분석 방법 등의 4가지 핵심 내용을 소개합니다.
Chung will present soft error tests for fast-moving automotive industry. At his last job, he spent more than 15 years in Cisco systems, and Mr. Chung also developed industry-first company-wide SEU test and mitigation process to mitigate radiation-induced soft errors. Sung is now with QRT Korea to lead R&D activities for single event effect testing and analysis technology. He holds 17 US and Korean patents and has contributed over 60 technical papers and presentations in ASIC test, design for test techniques, soft error test, and SEU mitigation, and fault injection techniques. This presentation brings 4 key points to address the status of various standards requiring soft error test, how the test is performed and the data is analyzed, where are the critical issues for the industry to manage the transition well.
ASIC 2021. This is the last session for the conference. My name is Chung. I'm from QRT Korea. My talk today is a software test for fast-moving automotive industry. In opening, I have a few reflections I wanted to share with you, which is based on quantum effect and the software on modern devices. It is all started about 110 years ago. As you can imagine, that black body was first studied by Max Planck in 1900, and he also the first person who coined the term quanta as well as a quantum. And the photoelectric effect was discovered by Einstein in 1905, and he actually understood and know what the quantum behavior is in terms of light. But he dismissed this idea until his death. Rutherford was the first person to model the atomic behavior and also the system which similar to the solar system we see today. The Bohr is the gentleman who actually developed the modern view of the quantum mechanics as well as orbital electrons for the atomic models. CMOS technology scaling trend-wise, and I think it is still following the Moore's law. And as you can see from the bottom, the references, the new beginning for information technology at the end of the Moore's law. I don't think it's here yet. It is very difficult to pin down the end of the Moore's law. We may have to wait a couple more years to see how it evolved. But in today's view, for next couple of years, the Moore's law is still kicking and screaming. Terrestrial radiation particles are the main sources for the radiation-related soft errors and the single event effect. And there are numerous particles we experience day to day. We don't know much about it because we don't feel as the particle pass through our body, but devices actually have quite different reactions from the neutrons and the muons and all the other particles coming down from sky. Dr. Kobayashi actually had a very good information on how the scaling trend of the digital single event effect will move forward. And his idea is there is no good news for you, and things are getting worse as we speak. Alpha, as well as the galactic cosmic rays and the terrestrial neutron is the main particles that actually produces CMOS digitalizes a single event upset, single event transient, single event latch-up, as well as a single event functional interrupt. What is the latest driver? Let's look at what's going on in the industry and especially for the automotive safety-related issues and highly reliable devices. The U.S. started Artemis program a couple years ago, and the Republic of Korea joined the 10 nations to participate in the program in recent days. Troubling issue is Moon also has radiations. It has about 2.6 times higher than International Space Station, and we have about 200 times more radiations than the surface of the Earth. It is almost the same as you are getting the X-ray all day long, which is not really good. Main particles coming down to Moon is the protons and the helium nuclei and the other particles. You are wondering why there are so many protons, because there is no airs in the Moon. And in the case of the Earth, there is air molecules actually break down the protons and then shower down the neutrons by cascading down to the ground, which is the one that actually we have on Earth, which is about 13 neutrons in New York per square centimeter per hour. SSD and high-density DRAM modules are the new incarnation of the changes that we have seen recent days. Samsung announced the new CXL-based DRAM modules, and CXL started from Intel, and then there is 2.0 versions that came out, and then there are a lot of promise and the complexity involved with this new incarnation of the high-density storage devices. Right inside is the Micron's new development in fresh device. As you can see, the comparison between the how high it is to the Eiffel Towers, and there are a lot of advantage of integrating the high density of the fresh memories in one single device, and saves energy and improves the efficiency and the throughput of the device as well. The notable functional safety standard changes in many years after the ISO standard came out in 2018 as the approved standard. And NC UL 4600 is already been approved and published. It also the improve the functional safety by emphasizing the autonomous safety of the vehicles and the related products that are used by the peoples and the industry. So TP is also going through the process of being approved. Other standards are already being existed to support the UL and the ISO, and that's AECQ 100, JEDEC JSD 89A, which outlines how the test has to be done, and as well as what the limit of the requirement of the test you have to perform. One of those, the changes that actually impact the telecommunication devices, ITU K130 telecom radiation test requirement. It has been approved. And then less of acceptance for now, but I think it's coming into an age when the automotive industry start to accept the communication side of the requirement, which require additional testing for the radiation test. The other test requirement on the bottom actually shows supporting nature of the testing for the devices that are going into automotive devices and the systems, which is from military, aerospace, as well as the jet extended committees. What will be the demand for the radiation effect scientist? We've been talking about having radiation test has to be done, but how many people actually have ability to do so? What kind of institutions actually supporting it? How difficult it is to have the engineers and scientists to carry out the required the exercise and the research and the development and testing for the radiation effect. The better version of the article is shown in the bottom as Vanderbilt University professor Ron actually outlined very good detailed requirement of it, but I just summarize the 3 slides here. There are growing demand for the radiation effect scientists and the engineers, and not only for the testing side of it, but also verification and the simulation and the testing and the research side of the radiation effect. The one that we have to pay more attention to than any other the area is the terrestrial reliability. It's automotive related and the aerospace and those areas. The next one is space and the defense and the accelerators, which actually does a lot of basic researches to have more greener, better energy sources for next generation. This is a summary of the radiation effect engineer's job and requirement for job skill set. Starting from the left side, extreme environment, all the way to the mission critical systems. And there are individual requirements for the given area. The modeling of the defect and the radiation transport, the energy deposition modules based on the various simulation tools, and the TCAD is notably used widely, as well as the physical layout and plastic models for putting the devices into a board, and also lay out the devices on the silicon system analysis, Bayesian models, and all the other stuff is also a critical side. And not the single person to understand entire spectrum of it, but also it actually connect the dot between each technical areas, so that understanding of the flow of entire area will be the radiation effect engineer's job and then job skill set. The connection between the experiment and the modeling, if you are the radiation engineers, are very important. Radiation test facilities normally provide approximations to actual environment. We do a radiation test of a neutron for the devices in order to mimic the terrestrial neutron effect on the device. But radiation facility actually provide the approximation of the environment, but it is not the actual environment. So testing performed, analysis is done, and extracting the information out of the reliability requires a lot of good information and the analysis mechanisms in order to make those data more relevant to the actual environment. Radiation effect engineers need to understand how the task is related to the application, like facilities, the devices, and the models they use for the testing and the analysis, and even the design of the device itself. Let's look at the emerging issues of what we are facing for the single event effect. We normally look at the soft errors more than anything else. Now we start to see the hard errors as the main issues in the destructive event, not only for the DRAMs, but also from the NAND flash memories. These are the few examples you can actually see the hard destructive event become an issue that we have to pay attention. when you look at the cross sections, it's E the minus 17, but it is a really higher number than before, and then it is getting worse. The stock bit in the non-fresh is also the big issue, but remember that the ECC and the other provisioning provided by the SSD, the filters these issues, but you have to maintain those, and the algorithms and how the SSD is provisioned through the SoC is the key issue by understanding how you can mitigate, correct, and also suppress the happening of these issues in NAND flash itself. MCU and the lot-to-lot variation is known to us many, many years, but multi-cell offset is almost the same as the single-cell offset in SRAM devices in the latest version of the SRAMs introduced. So the total combined single event offset rate for the device is the sum of the single cell offset and multi-cell offset. So and half and half. So it's going forward. You have an issue of ECC applications where the multi-bit is more than 2 bits, and you have to figure out how to mitigate those issues. The SCL variations for the given DRAM devices, as you can see in the bottom two pictures, is widespread. Even the threshold energy is different, and then also saturation energy to get to that point is also different. That means if you pick some device and you actually key on those devices, test the result, that might not going to be correct because the lot-to-lot variations are a lot higher than before. Now let's introduce a new test we developed at QRT, experimental radiation test systems. I'm going to briefly go through the nice pictures that I can share with you, but details will be discussed next year and the papers in coming days in IEEE or other conferences. For now, today, I will go through basic experimental test data and the system itself. The left-hand side, you can see the architecture of the system is a generic test, and then it will perform many different types of radiation tests. Right-hand side is experimental dosimetry board, which has 41 SRAMs. And the left-hand side, and the bottom, which is the beam profile informations we received from the lens. And you can see about plus minus 10% deviations from the location where you put the devices in. Right-hand side is actually we put the dosimetry board on top of the opening of the beam profile. And as you can see, there are different values in the soft error rate. The numbers given in here is arbitrary numbers. So you can see the slight differences in between those, even though the device intrinsic soft error rate is different, but it will show actually the differences between those beams and those from the device itself. And this is more precise information here. You can see the left-hand side, device type A and device type B. Distinctive differences between the location and between the type A and the type B. And the distribution of the device is also the map to the location of the device in the beam profile itself. And then we had some experiment with the SSD test, and then we can show you some of the experiment we have done from the test. The left-hand side and the two graphs are the power signature during the radiation test. You can actually see the where the system hang and the restarted, and then continue the operations after system restarted. As you can see, the multiple cycles of power on and off is given, and the signature of the individual, the read and write operations are also given here. The upper one is the write operation. and the one in the bottom is the reader operation. There are distinctive characteristics of the power signature is given. So we have done more precise analysis, but we cannot display this today's presentations. Right-hand side is the one that actually given by the NASA presentations, and then before and after neon heavy ion irradiation. As you can see, that each the areas of the fresh device actually error rate increases. And the same device, and right-hand side is the collimated beam from Los Alamos ICE-2, and we actually irradiated certain sections of the SSD device, and we tried to analyze soft error dependency between devices and the soft error dependency between the 2 or 3 part or with entire SSD. So we have a very distinctive the relationship between the individual pieces and who owns more the soft error related issues, how the soft errors in individual devices get filtered or they're corrected. The left-hand side is the FFT spectrum of the power signature. As the device gets tested and more errors accumulated in the SSD, you can see device frequency of the operation change. You have 249 Hz to 50 Hz as the device has more error accumulated in the slow down the operations and the performance of the device. And each one of those activities, we can analyze this in the spectral view of the signature of the power signals. So we have done SiC device in a similar manner and the same location as Los Alamos. And the left-hand side is the presented from other papers listed in the bottom, which is done at Rad Saga. And this month, I think it's early last month. And the shows the pretty well-correlated cumulative density function. And also right-hand side is the different voltage level has different rate of soft error rate, which means the SiC has very distinctive signature dependent soft error rate. The paper actually mentioning about the silicon has reached its limit, mainly because of the critical electric field, the operating temperature, and the switching frequencies are not even near to the SiC device. And it cannot match with the performance of the SiC. But SiC still has a lot of issues we have to solve. But SiC become a choice for the automotive industry because it reduces the weight and also the cabling of the devices and increases the performance of the device, meaning that for a single device actually has more higher efficiency than regular silicon-based power devices. These are another example of the voltage dependency of the single event, the burnout. As you can see, the 3 different devices have the different characteristics, and then voltage difference between 100 volt out of 1200 volt the rated device, you have the difference as well. And the left-hand side has a distinctive view as well as the right-hand side. And it's all well correlated and highlighted. So individual, the dot or the areas that we plotted is based on the burnout time or burnout affluence based on the testing what we have done. When I look at the trend of the device soft error rate as we close the today's presentation, soft error test becomes more complex and difficult. There is no doubt about it. In the beginning, I mentioned Dr. Kobayashi's trend analysis. I can encourage you to go look at those papers, but there is no good news in the papers. Actually shows the trend is continuously worsening as the Moore's law continuously driving the devices. The projections are based on the various data points, and as you can see, the percentage of the multi-cell upset is started at the 2016 about 100%, and ever since it is 100%. What that means is the 50% is a single bit, and the rest of the 50% is from multi-bit upset. Multi-bit upset is from 2-bit all the way through the range of the devices and the data bits, which means if you have a 16-bit data width, then it will have a 16-bit multi-bit errors. And the 2 or 3 will be more than the other ones, but there is always a case where the multi-bit can happen for entire word the lines. Mostly it is from a single event functional interrupt, but also there will be other phenomena that can affect the multi-bit areas. And the other gate-related error rate, expected values, and other trends are given here. So you can actually reference to, there's nothing that's getting any better in the near future, as you can see. And especially what we have to worry about is the AVF analysis becomes prime importance for the SoCs, which contains the microcontrollers, and it is difficult to manage microcontrollers to perform a radiation test because softwares and architectural differences between each operations based on the softwares and the architecture of the microprocessor itself actually provide the different vulnerability factors based on the functions, based on the architecture itself. So those are two key functions have to be analyzed through a different set of test vectors, and performance-related test algorithms has to be used. It is pretty extensive testing, but you will never get down to the bottom of it unless you have to have extensive analysis, and the simulations has to be done concurrent with actual device testing at the same time. This is the last slide. It is eye chart in a sense where there are a lot of information given in here, but basically what I'm trying to relate to this one is different devices, different the issues in the coming years. The things that you have to pay attention for more than anything else is SSD and CXL DRAMs, next generation high performance storage device will give us more performance in terms of usage, but also create a lot of issues for radiation testing. Another one is SoC and SiP devices, and so-called AI devices used in the automotive and other areas. It is hybrid of the devices in one package, and it will create a lot of different testing issues as well. SDC is also the big issue. I mentioned a couple of them. It is AVF and SVF, and ACE analysis, algorithms, and methodology has to be standardized and has to be developed. In conclusion, the key drivers for soft errors in automotive industries and the green energies and the functional safeties are the key drivers. And those areas that actually produce more new devices, and the new devices require a lot of testing and validation in terms of the reliability and the functional safety itself. So I summarize in the 4 words. And as we stand, the functional safety actually drive the auto industry. The auto industry is transitioning from a traditional all the way to the electric vehicles. And there are many different variations of electric vehicles, and the autonomous driving capability in the electric vehicle is also the issues. And then there is also flying vehicles that not only drive in the road, but moves the people up and around the sky. And that is coming up, and there are a lot of the development and the testing is done. The limited radiation beam facility is one of the bottlenecks that we face today. And as we go moving forward, and there are more devices for testing, and then the become the radiation beam facility become the bottleneck for the device testing. And I can see the limited the availability of the beams in U.S. as well as Europe and Asia, because the terrestrial applications require the neutron radiation facility, but there are not many facilities to perform the test that requires the standard based testing. Some of the devices are very hard to test, especially for the SoC and the SRP device, and the smart storage devices actually contains SoC inside. It filters and masks a lot of soft errors and hard errors. So you may not gonna see what's inside because it's almost like a black box. So functional complexity actually adds a lot of complexity to the test in order to improve, identify, and then mitigate from the design standpoint and understanding the issue in the long term, the relationship with the reliability and the longevity of the data centers on the automotives, and as well as whatever the equipment that uses these devices. So those are also all depending on the radiation test data and the analysis result to improve upon. So those are the key problems we have to solve. The last three, software get worse, and I mentioned a couple of times earlier, and almost every slide, software is not getting any better. Difficulties is there, device is not really any better, and the complexity of a device is worse, and the scarcity of finding the right person to tackle the issues, not only for the testing side, mitigating, implementing, analyzing, and also developing the software to work around the real issues in functional safety. So those are the 4 issues that where we stand today. I wanted to say a special thank you to those who supported and sponsored ASIC 2021 and made the conference successful. APSI from Korea, and the Kyungsung University from Korea, Los Alamos, in New Mexico, Los Alamos, USA, and also participated. NVIDIA San Jose, USA, also participated. And the QRT, as well as SK Hynix USA, also participated in our program. And also there are 2 government organizations sponsor this program, and I'm happy to have those sponsorships. Those who give us fund, as well as developing test systems for the industry, as well as a generic use for the next generation devices for automotive applications. If you have questions, please leave your questions online, and we want to get back to you, and answers will be posted on the web. And I wanted to have as many questions as possible, and I wanted to be interactive, but this is online conference, but yet we have a limited way of interacting directly with you. So we are really interested about getting your questions, not only for the technical issues, but also in general, questions will be welcomed as well. Thank you very much for your attention, and I'd like to see you in ASIC 2022 next year. Thank you so much.